All right, there we are. Hello. I'm wearing my another rainbow hat, so I'm sure Damon is jealous of all the ways that people have crocheted hats for me.
Just a little bit.
I wanted to, I'm hoping, Damon, you're going to be inspired and, make something. Because, once you guys start wearing the crazy hat days, you can get a bonus point for impressing me. But you'll have to have your camera on. I wanted to go through a couple things about the labs. So today is Thursday, which means it's lab day. So first thing is, hopefully you can see my board. If you can't, let me know. But you guys need to make sure you're responsible to check Blackboard, the grade book, because there's a couple people who haven't turned in something. I don't think it's anybody here. And you would know when you look at your grade book, because there was somebody, I think it was on Tuesday. No, it was on my other class. And you need to make sure your assignment submits, because Blackboard's been having issues. So please make sure you're responsible in that way. So labs. So lab 2 was the factor label lab. And the thing I wanted to mention about that is the people who did get the 15s all made time to come see me last Thursday. Some people were with me for like 4 hours last Thursday. And we went through the lab. So I made a note to many of you, make the time today or next Thursday or one of my office hours. And with that, because a couple people told me they have class on Thursday evening at 6, I'm going to move my Thursday night office hours up to start at 5:30. So you could always stop in before you go to your math class. I also, on Thursdays, because we get done early, I always stay on this until 1 o'clock unless nobody's here. So last week, a lot of people stayed actually until 2, and we worked on the math. All right, the lab today, it's a little messy. You're getting to work in your kitchen. The two big things with that is on the first page, when you do the math, do the best you can. If you have a question, just stop in my office hours. You are going to be limited to 2 sig figs because how you're doing the measurements. So when you get your final answers, just round it because you're estimating so much. And that's the idea of sig figs. The other thing is I mentioned about the pictures. Try to limit yourself to 4 or 5 pictures. So a couple people have already told me, oh, wow. But if you have 10, 15 pictures, you can probably look through them and see that several of them are repeats. So like the density tower, just send me your best picture of that. So try to limit yourself. Blackboard will also be happier. If you know how to embed them, that's great. Or else you just upload them and don't submit until you've uploaded it. And then the other thing I wanted to mention is lab 4. And the reason why this one is due next week, but it is there now. I opened it up today. It has 3 parts to it. One part is the electron stuff we're doing today. So it's more practice with that, so you master it. One part is a little kitchen lab. And one part is a 7-day challenge. And so because it's 7 days, the lab I made due Saturday, next week Saturday, if I click the right buttons. So you want to make sure you take a look at that lab. I would look at it today or before Saturday. I'll send an email out so you can start your 7-day challenge and have fun with it. So it does make a difference. And then a reminder, with all the labs and study sets, you can turn them in late for a 1-point deduction. You have until the midterm. The midterms in like 2 weeks on the Tuesday. And so we'll talk about that next week. Is there any questions about the lab stuff? So please look at the lab. Next week's folder is opened up. And so there is in there a review for the midterm. And so we'll do that either Tuesday or Thursday. All right, I am going to share my screen. And not that one. All right, we are going to go over the shells and subshell stuff. So Spencer asked me a really wonderful question this morning, and he said, you totally lost me. And there were some people who stayed after and made this a similar comment. So I had covered that on Tuesday with the anticipation. I would go through it again today. And when you do your study set, it should hopefully start making a little bit more sense, and we'll go over the study set next Tuesday and we'll do a review, and it will end up, I know it's hard to believe right now, it will end up being your comfort zone, your security blanket on the midterm, believe it or not. My other class is a little bit ahead of you because they have more hours. Yeah, and they all seem to have gotten it except one person. And so if you're having trouble, please make the time to come. I'm here before class on both Tuesday and Thursday, and you can be half asleep. All right. So this is all about where we're talking about the electrons. This page is the theory page. And again, you can go back with a different color and add things that we missed. The shell is the traditional way. This, again, is Bohr's model over here. I don't know. I edited your page, so I don't know if your page has the same pictures. But he only had hydrogen, so they basically had the electrons going like that. But our understanding now is that electrons exist in shells or layers. So it would be like onion skin. So these are like layers, and n is always a whole number. I don't like this pen. So as you increase the n number, you increase the distance from the nucleus. So this would be layer 1, 2, 3. And kind of back to the question you'd asked, Spencer, when we do this with the periodic table, writing notations, or at the bottom of the page, that's like these numbers in front, the 3, the 2, the 5, the 6. That's which layer you're at, or which floor. It's just a three-dimensional, because it's an atom. And we think of atoms as spheres, roughly. Really, they're vibrations, but it is in a spherical pattern. The other thing that n tells you, and this is actually important, is as you increase the n, you increase the energy, or it's actually the momentum of the electron. So the energy of the orbital. So the third layer has much higher energy, and that's what a quantum jump is. So if an electron is here at the first layer, it has low energy. And if we put a lot of energy in, so like the demo I did on the rainbow video, so when I lit it on fire, we put enough energy in, and so the electron will jump out here. It can jump anywhere. So that becomes a whole nother question to ponder. Because originally when like in this picture here, it shows only electrons there. Anything is possible. And so once the electron jumps out here, it's now in the third shell, even though there was nothing there before. So was the third shell there? But the potential for it to jump there is. And so something to ponder. And then this now has a lot of energy, lots of energy. It does eventually calm down, but it's not like you and me where we crash and it feels like we crash big, but it can only jump to here or to there. It can't go anywhere in between. And that jump equals, so this jump is a change in energy. And that change in energy, that was one of the things in the talk that I did that I videotaped in rainbows. I started with wavelength because that's where they started with that all the colors we see do correspond to a different wavelength. And then they realized those wavelengths correspond to a different frequency. So that's the previous page. So depending on the wavelength, you have a different frequency, and then that frequency corresponded to a specific energy. When we look at an electron, we're going the same thing, but the opposite direction. This change in energy when the electron leaps in corresponds to a frequency which corresponds to a specific wavelength, and we see that wavelength as a color. So we can actually see this is why we see fireworks, that the electrons get excited, and as they come back in, they can only make certain jumps. And so every element has a characteristic color. So like strontium is red, calcium is orange, boron is green, copper is blue, and anyway, that's where I was going with that we looked at it with light, and it turns out electrons behave the same way because they can only be at certain levels. The other thing that N tells you is N is always equal to the number of subshells. So that's our next layer, is the subshell is the shape of the orbital. So all of these are S's that are drawn. Typically, that's all anybody ever illustrates, but it is, the subshell order is SPDF, and you're going to see me keep writing this every time I'm teaching it. And so those are the names of the subshells. It does go on beyond the theory. These were the names. When a hydrogen electron is excited, it can only drop certain ways, and the colors you see are red, green, violet, and so they called them certain names, these 4 lines. And so again, I talked about, it's like playing a piano. You can only see certain changes. Rainbow, you see every color, and so that's called a continuous spectrum. All right, so it's the shape of the orbital, and as you become more complex in the shape, you increase the energy. So 2 things determine the energy: the N number and the the subshell. So S's are spheres, P's are the figure 8, D's are 4-leaf clover, and F's are really complicated. But this piece, that this also influences the energy, becomes important for where we're going with the periodic table. All right, what I started to write down is 1357, and this, when you do, by the time you get done with the homework, you just know it. You just write it down, SPDF. As we build with the periodic table today, we're going to keep referring back to this. The 1357 is the number of orbitals possible in the subshell. So a sphere, there's only one way you can draw it. Infinity sign, it turns out there are 3 ways because we have 3 axes in space, so the X, Y, and Z. A 4-leaf clover, there's 5 different ways they can draw it, and whatever I drew there, apparently there's 7 ways you can draw that mess. And then it keeps going, and computers can make beautiful drawings of how this is. Orbitals are fascinating because orbitals are the electron's path, except there is another word in there, and I don't remember if I did this with this class. It is the probable path. And this is, if you're familiar at all with some of the history, Heisenberg's uncertainty principle, which got expanded on. But it is, we can't know 2 things about the electron. The electrons are probably behaving like this. I did mention this, and this is probably why, like somebody's laptop went out in the last class and they sent me a message. And so because our computers work, it's why the computer age, why the technology age is all based on quantum theory, which behaves very different from the visible world that we see of matter. So once we get to the quantum level, it's because it is behaving like waves. So these are probability waves. And they knew it was a wave function. And it was another gentleman, I'm not going to remember his name, who said, well, they're probability waves. And that's where it all became crazy. But these are a diagram of the orbitals. And then the next level is the electron spin. And electrons, again, are little balls. So it's like a basketball. You can spin on the axes. So the spin is on its axes, clockwise or counterclockwise. And that's what we show by an arrow, up or down. So there's only two possible spins. And that means two maximum electrons in any orbital. Because charged particle, when it's spinning, behaves in a certain way, and there's only two ways it can spin. It doesn't matter if the up arrow is a clockwise spin or a counterclockwise spin. It's just that you can only have two possibilities. All right, we went through this, but I want to walk through it again because it is the theory. And the homework, do it the best you can. It's just questions to answer. Half of the homework is back with subatomic, so protons, neutrons, and electrons and mass number. But this again wants us how many electrons. So back up to here, SPDF, Ds have 5 orbitals. Every orbital holds 2 electrons. So that's why I wrote out 5 orbitals times 2 electrons. You don't have to show me the math, but the answer was 10. Here, as soon as it says orbital, this one's a subshell, it says orbital, the answer is 2 electrons. And then the third principal energy level, the shell, means you have the 3s, the 3p, the 3d. We always designate it by both the shell and the subshell because the third shell has 3 possibilities. We always go in order. There is no such thing as a 3s. And this would have 1 plus 3 plus 5, which is 9 orbitals times 2. Electrons, so 18 electrons total. And again, on this next one, the 2D is the one that's not possible because when n equals 2, you can only have the 2s and the 2p. There's no such, you can't go past that. At the second level, you don't have enough energy to be able to do this complexity of a shape. At the third level, you don't have enough energy to do this complexity, and so on. So they're limited to what they can do. Probably the most missed thing on this question is the 6G, because people are like, what is G? It's just the next possibility. This is all based on what is possible. They're actually there on the periodic table. The ones that are out there that you can see only go, it's not on the periodic table yet. Because these things only exist for like less than a nanosecond. All right, so now we're going to put it with the periodic table. And you probably don't have enough space on this. This is another gentle reminder. You guys are going to be doing a paper for the class and a presentation. But again, that's 2 months off. So you pick an element from the periodic table, or if you want to do a subatomic particle, so if you're like, I want to look into the discovery of the electron or into muons or something, that's possible. And it's like 3 pages. So, and then we're going to do presentations. I'll split you guys into 2 different groups, 2 different times. So it'll be about 11 people in each presentation. So I'm going to go back starting at hydrogen. This is a question, and a couple things. The configurations we're going to do, again, are NLX. The N is the shell. So 1, 2, 3, 4, 5. The L is the subshell. In the math equation, that was the variable that Schrodinger used. And the X is the number of electrons. And the other way we're going to do it is box and arrows. Again, these have different names online. The box is the orbitals. And the arrows are the electron spin. So they can spin up or down. So from the previous page, this gets us through the 4 levels. The thing that's actually beyond what you need to know, Schrodinger's original equation did not incorporate electron spin. That was somebody else who brought it in a couple of decades later. Maybe not that long later. And that actually allowed them, no, it couldn't have been that long later, but that allowed them to understand the whole thing and put it together. All right, and you're going to always show both, but like on the homework, I think there's only 4 that you actually draw out. They each have their purpose. They each will answer different questions that we'll go through. And again, a lot of people are like, whoa, you just blew this at us in like 10 minutes at the end of lecture. And I just wanted you to expose you to what we're going to look at today, because sometimes it helps to see where we're going. So this one is the atomic number, and it is the protons, but it is, at this point, the number of electrons. After the study set next week, I am going to start talking about ions, and then one of the days we'll also do a review for the midterm. Once we make an ion, the electrons will change, but for your study set, the electrons will be the atomic number also. So you always do, the most stable means you always start at 1, and we just say 1s1. So this is in the first layer, and it's just moving in a sphere, and there's just 1 electron. So for box and arrows, we just show, you can show a box or you can show a line. Some people like boxes, most people like lines, and this arrow can spin up or down. Again, clockwise or counterclockwise, it doesn't matter. So we're going to skip to lithium. So lithium has 3 electrons. So we would put 2 in the 1s. That's what I wanted to do. SPDF 1357. So again, SPDF is your subshell designation. So we're in the S. And 1357 is the orbitals, or the number of lines that we're going to be drawing, or boxes. So S's can only have 2 electrons because they only have 1 orbital. So this would be my 1s. So once the 1s is full, we have to move into the 2s and put 1 electron there. So that's my 1s, that's my 2s. All right, let's skip over to boron. So boron's number 5. Always miss doing that one. So same idea. We put 2, you always start, well, not always, we're going to do a shortcut today in a few minutes. Then we put 2 in the 2s, and then the second shell has p's. So it has, we go to the p's. So you don't have to write all this down, but when n equals 1, at the very beginning, the lowest is the 1s. When n equals 2, we have the 2s and the 2p. And then when n equals 3, so then we go to the next layer, 3s, 3p, 3d. When n equals 4, and goes on and on. Oh, wow, I wrote p, s. 4s, 4p, 4d, 4s, and so on. So in the first layer, I just do the s, and then I have to go to the next layer. But when I get into the 2s, I can go s's, and then I go to the p's. When we draw these out, we draw the whole thing, the 1s. I label my lines. You don't have to, but it helps many students. So there's my 1s, there's my 2s. And then the 2p, because p's have 3 orbitals, we show 3 lines. So it's basically like you guys hit the jackpot, you have a 3-bedroom apartment, and there's only one of you. There's only one electron. And so that electron can sleep in any room at once, head up or head down. It doesn't matter. So you can put it anywhere you want. Again, chemists and physicists usually write them as half arrows. It doesn't matter to me if you show a whole arrow or a half arrow. There's only 2 ways you can show the arrow, either up or down. It's just how they decide to designate it. Again, that represents the spin of the electron. Now, if we go to oxygen, so oxygen's number 8, similar idea, 1s2, 2s2. The reason I like to write this number here, that has to equal, these are our number of electrons. So right now I have 4 electrons, so I have 4 more, and I put them all in the P. So with the S, you cannot go past 2. But with the P, I can. So you could not put 4 into the S. So why can I go past 4 with the P?
You can have up to 6 orbitals or 6 electrons because
because
number
there's
of
3
orbitals.
orbitals. Damon's got it. There's 3 orbitals, which we represent by 3 lines. So you can get up to 6. We can do up to 6 there. Sorry. So 1s, 2s. It can help to label because it helps you to keep track of what you're doing. The 2p, you can bracket however you like, but you do bracket the p's to show they go together. And so we put 1 electron in each orbital. So this is what I did the other day, and we'll do a couple of these. When you have 3 or 5 or 7 orbitals, each one gets 1 electron because they're negative particles. They don't want to pair up, and then they start pairing up. So the 4th one will pair up. And so that's what we will get. This would be wrong. That if you showed it, so if you said this was your 2p and you put your electrons in like that, that is incorrect. They never do that. They don't want to pair up if they don't have to. But the reason we fill up the 1s, then the 2s, then the 2p's is electrons fill based on energy. So we are going from lowest energy to highest energy. And within a subshell, those electrons are all equal in energy. Different subshells have different energy, different shells have different energy. It's a combination of the two. All right, we're going to skip to sodium, which is number 11. So we start at the beginning. We do 1s2, 2s2, and we can put 6 in the p's. So again, it is this upper number that tells me how many electrons I have so far. So again, back to what Damon said, 2 plus 2 plus 6. So like Damon and Christian, when I ask a question, you guys are gonna have to start counting to 10 because you guys have so many bonus points to give other people a chance. But I do appreciate the participation. So trying to encourage other people to participate. That gives me 10. That fills up the first layer, the second layer. So now I have to move to the 3rd layer. So I'd say 3s1. And so 2 plus 2 plus 6 plus 1 more gives me 11. And that is my atomic number, which is my electrons. So drawing it out, oh, this gets tedious. You would do the whole drawing. I'm going to show you the shortcut because I'm think you're ready for the shortcut, because the shortcut rocks. And once you get the shortcut, this whole thing, the periodic table, I mentioned it the first week. The periodic table should look completely different to you than it did the first day, and especially after we get this piece. This is very special. 1s2, 2s2, 2p6. So a question, again, has to be someone other than Damon or Christian answers. What element would that be? And why? It's a two-part question. What element would that represent, and why is that special? Well, 2 plus 2 plus 6 is 10. And on the periodic table, element number 10 is neon. And the reason neon is special, it is a noble gas. We talked about this last Thursday. So that last column in the periodic table, the noble gases, so a noble gas is stable. As far as their electrons. So there's two places you can start. You can start always at number 1, but it actually tells a chemist much more if you start at the noble gas. And so the trick is you find sodium on the periodic table, and I cannot encourage you enough to learn your first 36 elements. You do not need to know the numbers, but to become familiar with the name. So when I'm saying sodium and then I'm writing Na, I'm not going to write the word out, that in your brain you see them as the same thing. So here's sodium. The trick is you can start at the noble gas that comes before the element. So we start at neon, and then we write it like that, and then we need one more electron. So on the periodic table, let's see if I had one I didn't write all over. I did last night. That the row, I think we talked about this, maybe not, but 1, 2, 3, 4, 5, 6, 7. Oh, you guys have a table on that page. That's why I wanted to print this out again, but we'll use this. Those counting down, these are the shell. The row number is the shell. And then it takes on another dimension, is the periodic table is actually this shape because of chemical reactivity, but they found that this all falls together, that these first two columns are what's called the S block. So that's why I put a table at the bottom of your page down here. So you can number down, but I'll draw down here like I have a table. So these first two rows, the 1s and the 2s, this is called the S block area. Over here, starting with boron over to neon, this is the P block. So it's called the P block. And back to the question that Damon had answered for me, P's have 3 orbitals, so they can have 6 electrons. And if you count from boron to neon, there's 6. And so what this is here, the first row has only 2 elements because the first shell has only the 1s, so there's only 2 electrons. And then here, lithium and beryllium are the 2 s's, the 3 s's are sodium and magnesium, the 4 s's are potassium and calcium, 5s, 6s, 7s. And then we can do the same over here. Starting here with the p's, there is no 1 p, so we have to start in the second row. We have the 2 p's, the 3 p's, the 4 p's, the 5 p's, the 6 p's, and actually your table had the 7 p's. My table is older, but the table on that page goes to the 7 p's. So the s's are here, the p block is over here, and then in the middle is the d's. So this is the transition elements is what they're called. So these are called transition elements. And they do something pretty funky. But they're also known as the D block. And that is going to allow them to do some pretty funky stuff after the midterm. They even do it now. And then at the very bottom, and this part varies on different tables, but it is 14-ish across. That's the F block. And the F block is really interesting because of how it fits in. This is number 58. It does go here. The table at the bottom of the page, some tables will actually put 57 and 89 down here, and some don't. If we were in person, we would all be using the same periodic table, which is this one I have here, which is much easier to teach with. But just be aware of that. Some put the 57 and 89 down here, and that's okay. But just the periodic table, they don't put these up here because it would just make it really long, and then it wouldn't fit on this page really nicely. But these are the Fs. So after neon, going back to sodium, here was sodium. We start with neon, the previous noble gas. We're going to do a couple of these. So Spencer, stay with me. All of you stay with me. We come down here to number 11. It's our third row. It's always S's that come after noble gas. So your row number, and then you just say S. So back to sodium, neon, and then we say 3S, and we just need the first electron for sodium. So just stay with me for like a half hour, and it will start clicking. And the thing that's really nice when you do the shortcut, oh, we only have to show the 3S arrow. The reason the shortcut is actually more important is this neon is called a core electron, and they do not react. They're stable. The noble gas core is stable. So sometimes they say the noble gas core electrons. This 3s1, this is reactive. And everything we're moving to for the rest of the term is we get to where we write chemical compounds next, and then we're going to write chemical sentences, or we put them into into sentences, writing chemical reactions out. So this one electron's going to react. You can probably guess how it's going to react. It's going to react because sodium is miserable having it, because if it could get rid of this, it becomes like neon. We don't symbolize it like neon because it has different protons. But that's where we're going, is that all the elements other than the noble gases either gain, lose, or share electrons to become like a noble gas. So they're trying to get back like their core. All right, so with that, let's do sulfur. So S is sulfur. Na is sodium. Again, you guys have tables with names on it. Other people do, so you might as well make sure you have that. Sulfur is number 16, and we're going to do the shortcut. So the key with the shortcut with the periodic table is you can't go backwards. It's a one-way. So you start with the previous noble gas. So we have to start with neon. So you can't go with argon and subtract some. You have to go to the one before it. This is number 10. And I know I've mentioned this. Again, the periodic table is not two-dimensional. It is actually a globe. Fluorine is right next to neon, so is sodium. And so I think it's on your next study set. There is the spiral periodic table, which actually shows that, and it drives students crazy. We're going to always use this. It's like taking when it's really hard to use a globe for most people, but if we flatten it into a map, a two-dimensional map, people can understand it for some reason. And we're in the third row, S. So we do the same thing. We say 3S, but this time 2, sodium, magnesium, and then we jump over here, and we're now in the 3Ps. So we say 3P, and you count your boxes till you get to sulfur. 1, 2, 3, 4. And another piece I forgot to mention, next to neon, you can write that neon was number 10. So you have 10 plus 2 plus 4, which is 16, and that was the number we were trying to get to. So this number that I write down here, that is there to help us as a checkpoint. That was a question you had kind of asked Spencer. All right, let's go ahead and do our orbitals. S, one line for the 3s, 2 electrons, and then the 3p, we showed 3 lines. Again, 1, 2, 3 electrons, and then the fourth one pairs up. So that's the 3p. So have another chance. See if somebody can get this one. This looks just like another configuration that I drew. Hopefully you did if you're playing along. My question is, what other element that we've drawn so far, there's not that many on our page, and why did it come out the same when we look at the box and arrows? Or why is that important? It's kind of an awkward question. Sorry, I'm looking for my green pen, which I found. Anybody?
Oxygen and sulfur, because they're in the same group.
Yeah, was that Christian?
Yeah.
Thank you. It doesn't show me who's talking for some reason. Zoom and Blackboard have limits. So if you look at oxygen and you look at sulfur, just looking at the box and arrows, they both end with 4 in their P's. So we have the same configuration. So it looks extremely similar to the oxygen. It's not the same because here we're in the 3p because we're in the 3rd row, but this is a question that you'll see probably 2 different places on the study set. What element behaves the same as oxygen? Anything in the same family. That's how Mendeleev made his periodic table. And it turns out when they got into electron configurations, they behave the same because they both have these 2 empty spaces. So with sodium's going to want to lose this electron. But for these 2, for oxygen and sulfur, they're going to want to gain 2 electrons. So if it could gain 2 electrons, it would fill these 2 holes up. And yeah, this is what my internet is saying, it's unstable. So if I disappear, so we made a choice. So Joey, several of you know my son Joey. I'm waiting for the next. I'm figuring this whole class is connected to my son Joey somehow. We made the choice that his computer is the one that's hardwired into the router, and we may eventually have to run cables from mine too. All right, so it gains 2 electrons. That's where we're going after your study set next week, because it would fill in those holes. All right, we're going to do another one. Let's do, and then I have to move to a blank piece of paper. Let's do potassium. So special K is potassium. We're going to do the shortcut. So what noble gas do we start with? Well, you find potassium.
Argon.
Fine. Yeah, and you find the one that comes before potassium, which is argon. And so we write argon. Now back to the question, Spencer, you asked me beforehand. I really like writing the numbers down here. These are the atomic numbers. So I'm at 18. I only have 1 more to go. So from argon, I come down from 18 to 19. So you guys know how to count. And it tells me I'm in the 4th row. So my other class, a lot of them have actually laminated a periodic table so they can write on it and then erase it. But make sure you have a nice periodic table. If you have a wall in front of you, put it up there, or also one that you can write on. And yeah, all right. So we're in the 4th row, the S block. We only need 1 electron. And again, back to the question I just asked, this looks just like sodium because they're in the same family. They reacted the same because their electron configurations each only have 1 electron in the S. So this pattern is actually shown on the next page. of your notes. Yours is shown smaller, but it shows that you have the S block, the P block, and the D block. Now, something interesting is going to happen with the D block is, so this is our 4 S's, which came after the 3 P's. So what happens to the 3 D's? Well, the D's are always knocked 1 row up. And that had to do with the pattern, the complexity of the pattern of, so from scandium to zinc, that's what it's showing here. From scandium to zinc is the 3 Ds. The complexity of the D pattern is so complex that it makes it a higher energy than the 4S. So the order the elements are in the periodic table, the order that these subshells show up also is based on energy. And that is how you're going to have to show your electron configurations. If we don't get to it today, when we do the study set on Tuesday, I'll mention that because there are places online that will show them different because they're trying to show something different. But the 4 Ds would be from yttrium to silver. So if I asked you, a question that you'll see sometime is, what subshell area is iron? So you hopefully know iron is Fe. Your midterm is during this time on Tuesday. It is timed. So you do want to be efficient, which means you're familiar with the elements. So you would find iron and you go, oh, it's right there. It's in the middle, it's in the D, but more specifically, it's in the 3D. If I asked for arsenic, it's okay, arsenic is AS. It's in the P area. So the S's and P's always go with your row number, so it's in the 4P. And it's absolutely legit to label your periodic tables so everything's there for you visually. If we were in person, what would happen as soon as I give the test out is most students would spend 5 minutes filling out their periodic table, and then they would actually finish the test even faster because they wouldn't be relying on looking through everything. If you study and go back and redo the stuff that I gave you, even though you got like 15s on your lab last week, that lab is really important. If you go back and redo your study sets and your labs, you'll do wonderfully on the exam. You won't have any issues with time. If you're sitting there trying to Google everything, there's no way you're going to finish the test. The other question that came up last night, is there a lab exam? Questions from the labs will show up on each midterm. So the first 4 labs we'll have done before the first midterm. So they kind of go, they do go with what I've been lecturing on. All right. So let's do a couple more. Let's do, actually, since actually let's do V. No, let's do Ti, titanium. So Ti is titanium, it's number 22. And then I'm going to give you a couple to try. Titanium is, noble gas that comes before it is argon. And then after number 18, we come here to 19. So then we'll be in the 4 S's, put 2 electrons. And then we're in the middle, we're in the D's, which are the 3 D's. And we would just have 1, 2. So we just write that down, that we start with argon. Now, if you stay after or you come to an office hour next week, don't say I'm totally lost, I don't know what to do. Come in and say, I need help with those electron configurations. I get this. Like, pick a specific one and show me what you can do, because you're not completely lost. What I find is everyone can always at least tell me what noble gas. So argon, number 18, and then after argon, and usually everybody can get that after the noble gas, we go to the S's. They always come after the noble gas, and the S is going to be whatever row you're now in for the element you're going to. I think the piece that trips people up is the D's. It just, the shell and the subshell together give you the energy. Again, this is quantum mechanics. It doesn't behave the same as the macro world that we see that Sir Isaac Newton put into mathematical equations. So the math is different. This is where calculus came from. Interestingly enough, Sir Isaac Newton's the one who invented calculus to explain a world he didn't yet even conceive. But 2 + 2 + 18 gives us 22. And then our orbitals, S, one line, and then D, this is again where the SPDF, D's are 5 lines. So SPDF 1, 3, 5, 7. Keep writing it because it's so important. That 5 is how many lines. You show all 5, but you only have 2 electrons. So this is a key piece. These 2 electrons cannot pair up until they have to. So until you get 1, 2, 3, 4, 5, then you start pairing. So these 2 electrons will go in separate orbitals, but there's a but, and this goes back to laws of magnetism. They spin the same way. You can put them in any 2 orbitals you want, but they both have to either spin clockwise or counterclockwise. So both arrows up or both arrows down. It's a law of magnetism. Again, I sat through a whole year of physics, 7th week, spring term, Fausto. Somebody asked him the question. He's like, oh, it's a law of magnetism. And everybody went, okay. The laws are there because they don't fully understand why. They know it's true. They make it a law until they can figure out why, and then they expand on it. And I'm not sure they understand fully why. They just know it is true. So they always spin the same. They can spin up or down. This is just a representation. So I'm going to give you 3 to try, and then we'll walk through them, and then kind of be like, okay, maybe it's a little better than last week. And then as we go through the study set on Tuesdays, you do practice. A comment for you, the lab I posted today, one of the pages, again, it's a 7-day challenge. You have to start by Saturday. So just make sure you look at it and pick one of them. There's 5 different possibilities. But one of the pages that you do have to do is more problem solving with this. It's actually a really tough page. You want to do it after we do the homework set. You can try it, but you want to do the study set first because it like takes this to the next step to see if you really get it. And you can absolutely come to office hours and get help with it. But I'm going to ask you if you did your study set first. All right. Let's do cobalt. Arsenic and TC. No, let's, yeah. Sure. So you guys are trying to do your electron configuration. Don't tell me you don't know how to do it. At least write your noble gas down. Try that. I'm going to have you also answer other things about them, or I'm going to. So I'm just making a note to myself. And actually, since we have the time, I'm going to also do RE. Never done that one. Should be fun. We're going to also do unpaired electrons. All right. So these are notes to myself that we're going to do for each one of these. If you guys are watching along at home, try it or go get a cup of coffee. I didn't pause myself because I forgot. Maybe I can for a moment. You guys try it. Maybe like 2 minutes. So Cobalt. Let's do cobalt as blue because cobalt blue is beautiful. So you find cobalt, and it'll be written out as a word. It will say cobalt. So you want to know it's CO, even though you have those little itty bitty words on there. And you find the previous noble gas. So cobalt's number 27, so argon. Again, these numbers are just a safety net, so we know what we're doing, that we got the right one, the right numbers. After argon, we come to 19, so we're in the 4s, so 4s2. And then we go into the 3ds, and you count 1, 2, 3, 4, 5, 6, 7 over to cobalt's box. Or you can add up. 7 plus 2 is 9 plus 18. Did I do that right? Yeah. That is 27. Sorry. So 4s, 3D, you show all 5. You can have fun with your bracket, make them however you like. Each box, each line gets 1 arrow, and then 2 of them will pair up. It doesn't matter which 2, but you have 2 that are paired. So talking about unpaired electrons, these are electrons or arrows with no partner. And so there would be 2 for this one. For titanium, it also would be 2. So I'm not asking how many blank spaces there are. I'm asking how many arrows do not have a partner. Oh, I'm sorry, that's 3. You guys are half asleep. My other class at night, they catch me really fast. So like next term, I switch to nighttime because I still make just as many mistakes. But all right, the HEO stands for highest. It's all capital letters because it's an acronym. Highest energy, occupied. I don't know how you spell occupied. Doesn't matter. Just go with it. Orbital. So it's the last thing that you're working with, which is the 3D. For titanium, it was also the 3D. You can answer that without drawing these out. For scandium through zinc, it's the 3D. For arsenic, it's going to be the 4P. It's whatever area in the periodic table it's in. All right, and then valence electrons. Let's do this with green. Maybe it's not going to show up. Valence electrons are the electrons after the noble gas. These are the ones that react. So it's the ones we're showing. So for cobalt, it is 9. It is all of these electrons. For titanium, it is 4. That's all it is. The valence shell is the electrons after the noble gas. They react. All right. So on the periodic table, that's really simple. So if I ask for, say, zirconium, you would say, okay, the noble gas was 36. We need 4 more to get to there. So the valence would be 4. All right, let's do arsenic. Arsenic, again, we start with argon. And anytime you start with argon, after it, you're going to say 4s2. And arsenic's way over here, so we have to go all the way through the 3Ds. When the Ds are full, they have 10. And then you're back in the 4Ps. So the S's and P's do go with your row number. The D's are the ones that are off. It just takes practice. And arsenic, sorry, this line would be here. We'd go 1, 2, 3 to get to arsenic. This staircase is for the metalloids. That's something different. So 4P3, does it add up? So we get 15 plus 18 gives us 33, and arsenic is 33. And you do show, there's my 4s, your 3d. You do need to bracket. If you don't bracket, that tells me you're hoping I don't count, you're hoping you don't, and also that you don't fully respect that they go together. 3 electrons, they all 3 are separate orbitals. They are all 3 unpaired. They either all spin up or all spin down. It's a law of magnetism. Not a rule, it's a law, because it's physics. In chemistry, we can make rules. In physics, they make laws. The HEO is the 4p. It's the last piece that you have any electrons in. The valence is everything after the noble gas, so 15. All right, so we move on TC. Noble gas that comes before technetium is krypton. Let's go back to blue. So we start with Kr, which is number 36. And now we're going to be in the 5th row, so the 5s. So again, after 36, you come to 37. And so if you're totally lost, just say, okay, I can get the noble gas. Previous noble gas. After 36, I come down here. You're always going to have an S after noble gas and the row number. And then the trick is just the piece I think that people get wonked out about is the D comes after the S's because we go down a shell to 4. And then you just count 1, 2, 3, 4, 5. So the question students have is when I write my little thing, I write SPDF. And they're like, but on the periodic table goes SDP. Actually, it doesn't. It goes 3S, 3P, and the 3D does come after it. It just, everything gets shifted. Again, we flattened this in 3 dimensions. It does fit with this much nicer. All right, and that's it. Our valence would be all 7 of these. Our HEO would be the 4D. Our unpaired is actually going to be 5. Now, some people can see that from this, but you always draw it out. So my 4S, the 4D. The students who draw it out, I'm sorry, 5S, 4D, we move down a row. 1, 2, 3, 4, 5. They're all 5 unpaired. You can show half arrows or full arrows. They all spin the same before they start pairing up. Questions? All right, RE is number 75. I don't remember the name. And technetium was 43. Odd numbers are never as stable. But we had 36 plus 7 got us to 43. For RE, we can go, oh, it's the same idea. We have xenon. And then we just come down here. We're now in the 6th row. So I got this, 6s2, 5D, 5. We're like, it's great. It looks just like technetium. We would have 7 valence, 5D is my HEO. I'll have 5 unpaired. Everything's going to look the same, except there's a but, and there's a reason I wanted to do this one, because it brings in a twist. So does anybody see what I'm missing? Well, if you take xenon, number 54, and you add 7, you do not get 75. You get 61. I'm missing 14 electrons. So 14, SPDF 1357. 14 electrons is the F's. And so that star there between 57 and 72, to get to RE, you do have to go through this row. The D's were 1 number off. And this is taking it a huge another step. I always end with the quantum leap stuff. The F's are always 2 rows off. So the 4 F's are in the 6th row and the 5 F's are in the 7th row. To show this, we would put them after the 6 S's is where the 4 F's came, and then the 5 D's. And we would show them in here 7 lines, and every line is full. Okay, I did it right. So the picture at the bottom of the page, you have different pictures than me, sorry. I don't remember what I did on this page, but I know you have this picture. This was there just to show you the different shapes. So S's have 1 orbital, P's have 3 possibilities, D's have 5 possibilities, and F's have 7. The D's, again, do come after the P's because they're shifted down. You can ponder that. I wanted to show you one other thing, and we can do it with RE. If you're like, you know what, I'm just going to Google RE and I'm going to do everything, and I'm just going to like Google, or those, my students last night, their bonus question, I could tell they Googled it. And there's some site you can ask them a question, and they got like these 2 Indian professors were arguing back and forth the answer. I can tell when it's not your answer. So, and then I get a red flag in my head about you. If you look it up online, they'll show RE as xenon, and then they'll show 4F14, 5D5, 6S2. And you will not get full credit if you did that on a quiz or test situation. We're going to go with this. This tells us a lot more, and there's a reason. I want to explain what they're doing there, but this is how they show it, or on your periodic table. Some people have fancy ones. What they're doing is they're showing inside to outside. So from inside to out, this is the outermost, the 6th shell. Back to the valence electrons, when the F's are full, they become stable, so they no longer count in the valence. But if you wrote 21 there, I would not mark it wrong, but I go with the 7 because these are the ones that are going to react. How we're showing it is much more useful, which is from low energy to high energy. So the 5D is the highest in energy here. So it goes 6S, 4F, 5D. And so that is why the HEO is the 5D. This is harder to see what the HEO is. The HEO is where most of everything's happening. And so I don't know who came up with this notation. That's all over online. It's been like that for a while. But you shouldn't have to use that if you go through and try it sincerely. Are there any questions before I stop?
Wait, why is the valence electrons on RE 7? I thought it'd be more, shouldn't it?
You could say 21. I would not mark it wrong, so I'll put that as a parenthesis. Thank you, Christian. So 21 or 7. When the F's are full, they become stable and not reactive. So it actually, we show them because they're not part of xenon, but they don't react at all. I never ask for one down in here. I might ask for one after it, but these guys do some really wonky stuff. The thing that's really cool about these are called also the rare earth metals, because there's not many of them, like not abundance wise. But because of the F's and because of this weird thing that's happening between the D's and the F's, these guys have a magnetic moment. These are what is in the really highly expensive electronics. So if you buy like really expensive headphones, they will have usually 2 of these, neodymium, and I think it's DY. But once they're full and we're back up here, yeah, when you pick your element, you should find something that has something really cool that you know nothing about. So some of these actually do really cool stuff. But once we're back up here, so you could say, so back to what Christian said is, why did I only say 7? If you said 21, I would give you full credit. If you just went with the 7, that is fine. And actually, you opened a can of worms. He opened it, not me. The same thing happens when Ds are full. So arsenic, if you go back up to my arsenic, the 3 Ds are stable. We show them because they come after the argon, but you could say 5 valence because only the S's and P's will react for arsenic. When the Ds are full, they no longer react. If they are only partially full, they're extremely reactive. They do some really crazy stuff. And then the F's do even crazier stuff. And now that they're at the verge of being in the G's, it'll be even crazier. Great question. Anybody else? All right, I'm going to stop and recording and sharing.